Okay, I think we can start. It's a great pleasure to have here Professor Riccardo Barbieri, which is a theoretical physicist, leading expert in the world on the physics beyond the standard model of elementary particles. He got his PhD at Scuola Normale Superiore in Pisa. Later he was at CERN for some time also as a staff member. And he later returned to Pisa, where he was professor at the university and at Scuola Normale Superiore. Firstly interested in high-order radiative corrections in QED, then he turns to QCD, and finally to supersymmetry. Among his results, I mentioned the first realistic model of supersymmetry breaking via supergravity, and the quantitative formulation of naturalness concept in supersymmetry models. His sentence, elementary particle physics is the quadrant of nature whose laws can be written in a few lines with absolute precision and the greatest empirical adequacy, is a good starting point to introduce this colloquium, particle physics after the discovery of the Higgs boson. So please.
I don't need that.
I to just
it? Yes. Okay, thank you very much for this introduction. Let us see what I can do. So the title, you see it. Allow me to start with the page which is in the Department of Physics, should not really be shown, I mean, is very well known. Is the collection, is the modern, what sometimes can be called the modern Mendeleev table, right? Is the collection of all the particles that makes the standard model. The only thing that I have added myself, I think you all understand it, even the students, right? If not, you should ask, okay? J equals 0, there is a single scalar particle, J equal 1/2, matter in 3 replicas, and J equal 1, which are the vectors that carry the interactions. I have included the date of the experimental discoveries, right, to the best of my knowledge, for every particle, with 2 exceptions. One is the photon. 1905 is really not the discovery of, is Einstein, okay? So it's not really an experimental discovery, but I thought that was appropriate. And of course, the other exception are the discovery, the quark UD, the 2 quarks that make the first generation, I say it for the students, right? And the quark S, for which I indicate the date at which the concept of quark was introduced, right? Because before there wasn't the concept, so I could not read. Otherwise, all are experimental discovery dates. And of course, the big question is this a complete story? No? Looks so, right? A single scalar, to me, there is a striking fact there. There is a single scalar, which is, as you see, very different from the situation of the other J equal 1/2 individual J equal 1 particles. Yeah, maybe interesting to see this, okay? This is the status in 1973 when essentially, thank you very much. You know what? My problem is that I normally don't see it. So I have a problem. My eyes are not tremendous, so I don't really see it. So, excuse me, I don't use it, all right? So, you see, that was the situation in 1973 when the model was formulated in its integrity, in a sense, right? And one even knew that there should have been 3 replicas. No, even the students know that is the first line is normal matter, so to say, and then the other lines are replications, right? Whose existence is a bit of a mystery, right? And we don't really know why. But in 1973, it was observed that we needed at least 3 replicas in order to be able to describe CP violation. And this observation was recognized with a Nobel Prize or 3 years ago. Okay, now, you see, this page is, I show it, I don't pretend that you understand it all, right? But I show it to substantiate the sentence that was quoted by Marchetti here, and because it shows what I think is the main nature of particle physics, the main characteristic of particle physics. Particle physics is a synthetic piece of physics, is a synthetic part of physics, right? We aim and we succeed to some extent to describe nature at the appropriate distances in terms of few equations. In fact, only one, right? That is the equation that contains all the evolution equations that describe matter at distances, say, below the atomic scale, okay? Now, I have indicated, you see, there are 3 lines. The first line, even the student who have seen quantum electrodynamics should recognize it. First line is really the line that describes matter and the vectors and their interactions, okay? I have indicated for every line the period during which each line became a piece of physical reality, in the sense that it turned out to be true, right? In the sense that we used to say it in physics, okay? So you see the first line, it took several times, quite a lot of time, but I think by the end of the year 2000, we knew that that first line was absolutely a good description of nature. Then there is the electroweak symmetry breaking, the Higgs part, the second line, and of course it started becoming more and more evident in 1990 during LEP, essentially. Indirect signals came to show that the Higgs, something like the Higgs, should have to be present. But of course, the coronation of the empirical evidence was the discovery of the Higgs that took place in 2012. Okay, and then there's the first line, the third line. The third line, you see, the index I denotes the 3 generations. You remember that there are 3 lines, right, in matter. We call them families or generations, and then the third line is the only line in the standard model that distinguishes among them. You see, the third line, the 3 lines, are characterized by the fact that the interactions are exactly the same for the first, the second, and the third line. The only difference is masses and mixings, masses, right? And that difference is described in the third line, which until the end of the past century, I dare saying that there wasn't really any direct evidence. Now the situation is improving a lot, and it's getting better and better, and I will tell you about that. You see, I would love to be able to comment on why we think that those lines are a piece of physical reality, as I keep saying, right? But that's not the purpose of the seminar. I have only written, a little table which shows, in the case of the first line, different set of experiments. APV stands for atomic parity violation. G minus 2 of the electron, G minus 2 means the magnetic moment of the electron, the muon, W and Z properties, mass of the top. The relative precision at which we are able to measure and calculate the various quantities, right? Delta over O means the relative precision, and then the typical distance that is involved in the test. So you see, there are more than 10 orders of magnitude in which we are able to describe what physics is. But as I said, the purpose is not really to focus on the evidence, right? It's more on the rest. Now, you see, I think it's important to understand that there is an alternative definition of the standard model which can be given in terms of principles, not of equations, right? Because, the key thing is not really economy in equation, it's economy of principles, right? That's what I mean when I say that particle physics is synthetic, okay? And the criteria are given there, you see. You have to tell which is the symmetry group. Symmetries, I say it in a second, are the crucial ingredient, okay? So far. Symmetries have been the crucial ingredients. Symmetries have dominated fundamental physics in the last century, right? So physics is the... So you have to tell which is the symmetry group, Lorentz times what we call an internal group, which is SU3 cross U2 cross U1, right? L is the Lorentz group, or more properly, the Poincaré groups, but these are details, okay? So symmetries. In fact, Lorentz is exact. G, as you will see, is spontaneously broken. Then you have to tell how the particle transform under the group, right? The reps, the representation of the group. For example, when I say J equals 0, J equals 1/2, J equals 1, I mean a particular representation of the Lorentz group, right? See below. Well, I'm not sure that I have further comment on that because I have to, that's okay. So you understand what it means, particle content. Is tell how the various particles transform under the symmetries. And finally, there is a third rule, right, which defines completely the theory, which says that all the operators which are product of various fields or derivative of the fields, or derivative in the Lagrangian, have to enter, so you have to write down all the operators of dimension less or equal than 4, with a single exception. I will come back to it, which is theta, G mu nu, G mu nu tilde. G mu nu, G mu nu tilde means the two field strengths of the gluon, right? Like F mu nu for the photon, G mu nu for the muon. The two field strengths contracted with an epsilon tensor, epsilon mu nu rho sigma, right? Now, for non-particle physicists, you should know that in particle physics we use units in which h bar and c are equal to 1, which means that the vector field or scalar fields or derivatives have dimension of mass. There is only one scale, mass, okay? So mass. The spin 1/2 fields have dimension of 3/2, and the Lagrangian density, in fact what I wrote is not the Lagrangian. The Lagrangian density has dimension of mass to the 4th, because integral d for x of L is an action which, since h is equal to 1, is dimensionless, okay? So you understand that there is a limited number of operators that you can write down, no? And this defines completely the standard model. Right, as I said, the key to the synthesis so far has been symmetries. And, there are several types. The concept of symmetry evolved in the past century, right? And there are several kinds of symmetries, discrete, rigid. Rigid means the parameter of the transformation does not depend on space-time, right? Local means, on the contrary, parameter like in QED. QED has gauge invariance, meaning that the parameter of the gauge transformation depends on x and t, okay, on x mu, right? Or accidental. Accidental is an interesting fact, on which I will come back. And of course, there are several fates for this symmetry. They can be exact, spontaneously broken, or approximate. You see, the history of the electron very much illustrates why symmetries have played an important role in allowing to be synthetic, right? You see, in the first 2-3 decades of the past century, atomic physics dominated. After the discovery of quantum mechanics, atomic physics, the spectra of the atoms was the key thing. And there were a lot of problems which were all solved by dictating that the electron, by recognizing or dictating the electron had two spins, right? And that the interaction were rotational invariant, okay? That brought a lot of problems to zero. So it took a doubling of the electrons to solve the problem. The same happened in 1932 with the discovery of the positron. I mean, Lorentz invariance says that there is nothing mysterious. Is a degree of freedom that is included in the electron, in a sense, by the fact that you have Lorentz invariance, okay? And finally, something that may disturb non-particle physicists. I mean, believe me if I tell you that in the Lagrangian of the standard model, which I wrote, there is no distinction, there is no way to distinguish between the neutrino and one helicity component of the electron. The neutrino and the electron, say it briefly. Okay, there is no way to distinguish in the Lagrangian, right? Of course, you can say, but you tell us that the neutrinos are capable to transverse the Earth, and the electrons, of course, you stop them with a piece of material here, right? How comes? Well, the key, so the fact that the two particles are really have to be thought as a single particle in a sense has to do with the electroweak symmetry, and the way to describe, to understand the phenomenological fact that the neutrino is very well different from the electron comes from spontaneous breaking of the electroweak symmetry, which is of course the reason why we thought for a long time that an Higgs particle should exist, right? I don't know if you have, I presume that you have been, in the last 2 or 3 years, everybody of you has been, has seen a page like this, right? You have this potential, this famous Mexican net potential, right? And although the potential is perfectly symmetric, right? If you transform H as a doublet of SU2 or you give it a phase, the potential is perfectly symmetric, right? But the minimum of the potential breaks the symmetry, right? So think of a rotation symmetry, is essentially a rotation symmetry in O4, right? In rotation in a 4-dimensional space, right? But it's a rotational symmetry. And clearly, that potential is symmetric, but the minimum, every point in the minimum is not, right? And the X is the excitation, the radial excitation is the excitation along the direction orthogonal to the various minima, right? And the explanation is that, at the minimum there is an X condensate, right? Whereas on top of that hill, there is what naively you could call the vacuum, but actually is not the vacuum. I mean, we call vacuum the minimum of the theory. So this is the explanation of why the neutrino and the electron behave differently, okay? Right, I think that as an introduction, yes, I want to tell you this, right, which is an interesting story about symmetries. You see, so field theory was introduced rapidly in the 30s already, right? And people wanted to describe quantum electrodynamics, okay? And soon it became clear that there were divergences, right? I mean, you computed observables and there were divergences. Now, the observation came in the 40s and in the 50s, and that led to the foundation of quantum electrodynamics, which is of course included in the standard model, right? By the observations that if you insisted on taking only the famous operator of dimension less or equal to 4, right? Only those little set of possible operators that you could write down, which are symmetric under the gauge symmetry, okay? But only the renormalizable ones. You would not get rid of all the infinities, but the infinities could be absorbed in the redefinition of the electron mass and the electron coupling, essentially. So that the problem of infinities, at least in that sense, was solved, and all other observables were perfectly finite. Now, a key observation came a little bit later. Well, who knows? I think Wilson understood it first, probably, right? That, in fact, there's nothing really wrong in introducing operators of dimension greater than 4, because, in fact, the prediction of the theory at sufficiently low energy, I will have to be more precise, but let's accept that, are insensitive to the higher dimensional operators, right? So the higher dimensional operators only introduce small corrections, right? Now, at the level which is an important development, right? Conceptual development. Why? Because it means that the space of symmetry is of Lagrangians is much bigger than the one that you obtain by restricting yourself only to this little set of renormalizable interaction is much, much wider, right? But that led to an interesting fact that if you stick to the renormalizable Lagrangians, right, you get accidental symmetries. What do they mean? You write down, following the rules, only the operator of dimension less or equal than 4, respecting the gauge symmetry, Lorentz symmetry, and as a consequence, you get further symmetries. Examples are parity in the electromagnetic interaction. You see, if you accept the rule of the game, you don't have to enforce parity to describe electromagnetic interaction. They come out as a consequence, okay? If you know what isospin is, isospin, Gell-Mann SU3, chiral symmetry in the strong interaction are also accidental symmetries, at least approximate. But perhaps the most important thing is that in the full standard model, as I have defined it, baryon number and lepton number are exact symmetries. What is baryon number? Is the number of quarks minus the number of antiquarks. There is nobody has ever observed a reaction in which the number of quarks minus the number of antiquarks changes from the left to right, okay? Any reaction, for example, that's why the proton cannot decay. The proton cannot decay because that would imply violation of lepton number and baryon number and lepton number. Lepton number is the number of leptons minus the number of anti-leptons. You know what a lepton is? The students, do they know? You know, the electron is a lepton, the neutrino is a lepton, okay? Right? And what it means anti-lepton, you also know, right? So those are exact consequences of the standard model to the extent that you do not include the greater than 4 operators. Because if I include greater than 4 operators, with suppressed effect, even baryon number and lepton number are not exact. Okay. You know what? I don't have a clock, but 1 second. Sì, 5:15, no? 3:15, 3:30. 3:30. I have to. Okay, I'm sorry. Now you see, this is in a sense the most charged page that I have, right? Which is a list of I think is a pretty complete list of problems for the standard model, right? Or question for the standard model. And I will comment not on every issue because I don't have the time, but I will comment on several of them, okay? So I like to show the page in all in one page because it shows that the standard model is not a complete story, first of all. This is at least what I think. You see, this set of problems is so clear and so important that shows that the standard model is not complete. The other reason why I show it all together is because I think that the nature of the standard model of particle physics, not of the standard model, particle physics, wants that one keep track of what happens in several fields together, right? You see, of course, the high energy frontier, nowadays the LHC is very important, is obviously, right? But that's clear that if you thought that particle physics is exploration of the energy frontier, you are wrong. That is shown by this page, okay? For example, you see, which rationale for Magter quantum numbers, you remember the representation of the various of the representation, right? The choice of the representation, which is dictated by experiment. There is a little problem. We don't really understand, I claim, why the charge of the proton plus the charge of the electron is less than 10 to the minus 21 E, right? We don't understand that, I claim, okay? And that's part of the problem of the quantum numbers. There are phenomena which are not accounted for, right? There is a partial list. I will comment on neutrino masses. You all know what dark matter is. Let me comment on the neutrino masses. You remember that I told you that there is one single exception to the rule that you should include all the operators of dimension d or less or equal to 4, right? And there are several. There There's one single exception, which is that term, theta g mu tilde. Theta is a dimensionless parameter, is an angle, but never mind. It's a dimensionless parameter, and experimentally we know that theta is less than 10 to the minus 10, as I will tell you, and that is another problem. As I said, the normal way to think of the standard model is that there are high dimensional operators, and the question is, what's the role of these other dimensional operators? And for example, I think that neutrino masses are an obvious manifestation of that, as I will try to explain you. There is the question of the proton stability, and then there are what I call lack of calculability problem, which is a euphemism, as you will see, they are main problems. Okay, let me try to comment. First of all, neutrinos, right? Neutrinos, first of all, we know from 1990, roughly, that neutrinos have a mass, and we expected it, I should say, right? Even though in the standard model, the neutrinos are, as I have defined it, the model are rigidly massless, okay? And the mass comes from the fact they are rigidly massless because lepton number is the same thing. Lepton number is exactly conserved, as I said, right? But in the ideology that accidental symmetries are not exact, lepton number is likely to be broken, and that explains why neutrinos have a mass and why the mass of the neutrinos is small, right? If you have followed me. Now, you see, we know a lot already about neutrino masses and mixing. We really know a lot. The only thing that we don't know is where is the mean mass, so to say, the center of mass of the. Let's say that there are only 3 neutrinos. I don't see any strong evidence against that, okay? In fact, on the contrary. There are only 3 neutrinos, and we know mass differences. I mean, we study them through oscillation, so we know mass difference, but we don't know where is the mass, the center of mass, so to say, right? Within 1 or 2 orders of magnitude. Now, there are 3 ways in which one can get to the neutrino mass. There are 3 experimental ways. Unfortunately, all of them very, very complicated, but also very, very important. One is to study the beta decay and look at what happens at the end point. This is an observation of Fermi. If you look at the end point in the beta decay, you should be able to get an evidence for a neutrino mass. There is what is called the neutrinoless double beta decay. Most of my colleagues know what that means. And there is a way to get a handle on the sum of the 3 masses, M1 plus M2 plus M3, in cosmology by looking at large-scale structures. Structures in the universe, you can describe them by what is called the power spectrum, the amount of matter at different scales, right? And there is a way to get that parameter, sigma. And you see there are interesting correlations. There are 3 possible correlations, 2 by 2 correlation between 3 parameters. And all what we know about neutrinos shows that you should live in this, in those areas delimited either by a red or by a blue contour, okay? This comes from current knowledge of neutrino masses and mixings. And the ideal thing would be to be able to make measurements. As I said, unfortunately, the green lines are hypothetical measurements, right? But the ideal thing would be to be able to make these 3 measurements and to see that the triple correlation works. As I said, these are very difficult experiments. I think that I know. But cosmology is making progress. This is relatively recent happening, which, as you see, limits sigma. Sigma is, for example, sigma is shown, for example, here, right? Or there, right? Or there, right? So sigma now, the best fit of several cosmological observations say that sigma is likely to be not bigger than 0.15 electron volts with some precision. And you see there is significant impact on the 2 of the 3 correlations that I told you, right? which is indicated by these plots, right? For example, and you see the message, for example, of the upper right plot, unfortunately I don't have a pointer, but that's my fault, okay? So the upper right plot shows that if you were able to go down to 0.05 sigmas, you should find something, right? You should find something. It's not inconceivable. It's not inconceivable. So cosmology is making progress in this direction, right? Cosmology, we know, is not dependent on priors, right? But I think that this is still highly significant and has to be followed. Now, second question that I want to comment on. Why theta less than 10 to the minus 10? How do we know that theta is less than 10 to the minus 10, right? Well, you see, it takes the observation that theta g mu tilde is T odd, right? Time reversal non-symmetric, minus, right? T odd, or CP odd is the same thing. And almost the only source of T violation in the standard model. Almost, not quite, but almost. Now, you probably all know that under time reversal, mu dot B, right, the interaction of a magnetic moment with the magnetic field is plus, is even, right? Whereas the interaction of a dipole with the electric moment is asymmetric, is minus, right? Now, experimentally, of course, we all know that, for example, the magnetic moment of the neutron is 2 10 to the minus 14 e centimeter. We measure it, there is no problem, and that is consistent with the fact that T is okay. T is okay, right? On the contrary, in spite of the intensive searches, there is limit on the dipole moment of the neutron, the intrinsic dipole moment of the neutron, which would show a violation of T invariance at the level of theta times 10 to, experimentally less than about 10 to the minus 26 e centimeters. You understand? There is a factor of 11, 10 to the minus 11, 10 to the minus 12, stronger than the measurement of on the magnetic moment. And that tells that theta is less than 10 to the minus 10, as you see, as you compare the prediction, right? If there is a theta, there is T violation, and in fact, there is a dipole moment at the level of theta 10 to the minus 15. So that is a problem, and in fact, of course, you could say, but look, I mean, if less is 10 to the minus 10, why don't you forget it and you think that theta is 0 and for some reason? Well, not quite. For various reasons. First of all, because in physics we are not happy we say that the parameters is 0 when we don't know the reason. But secondly, because there are many extensions of the standard model in which you do expect a dipole moment at the level of 10 to the minus 26. In any case, to solve this problem, which is sometimes called the strong CP problem, the strong T problem, the strong CP problem, we know a possible solution. The possible solution is make theta a dynamical field, which is forced in Higgs cosmological history to relax to 0, almost, and possibly appear as dark matter. So there is a way to take care of the problem, which requires the introduction of a new scalar field, not the Higgs, a new scalar field, which is called action. And I cannot explain you how that works, but this is an idea which has been introduced in the 70s, right? So is a absolutely sound ideas. The problem, you see, this is a collection of limits, right, on the action. Now, you see, on the lower axis, you have the action mass. Yeah, we don't really know where the action mass is, right? And it can vary if you can read it. It's not a very good... it can vary between 10 to the minus 7 and, at least in this plot, 10 to the 7, right? The scale is exaggerated, but in principle, right? And there is a one-to-one correspondence between the mass of the action and the inverse strength of the coupling, the inverse coupling of the action to, for example, to photons or to gluons, etc. And what you have to take out of this page is that there is a window which is untouched, either by experimental observation or by indirect limits that come from astrophysics and cosmology. And unfortunately or fortunately, depends on your attitude, is the region which is the most interesting region for the action to be dark matter. So you see, between around 10 to the minus 4 electron volt, 10 to the minus 3, 10 to the minus 5, that is the most interesting region. Yes, for example, this is the most classic attempts to search for an action. Is a kind, for those who know what that means, kind of a Primakov effect, right? This is a sketch of the limits that the most advanced experiment is able to set. And as you see, it's not easy for them to reach what I think is the most interesting region, between 100 and 1,000 micro electron volts, right? So a relatively interesting happening is that maybe there is a way to try to get to that area, to that region, right, by looking at the coupling of the action to the spin of a particle, right, which I show in the second equation. This is another equation that I've written. I didn't want to write equation, but allow me to do that in one case, right? So it's a coupling of the gradient of the action field, this field that pervades the universe, if the hypothesis is true, with the spin of any particle in principle, and which means that the gradient of the action makes it a kind of effective magnetic field which oscillates in time at the frequency, at the mass of the action. And there are people who are making an effort in trying to catch that coupling of the action wind to the spin of the action. This is a sort of a collection for experts of the attempts that try to get this coupling, and I wanted to show it because even in Padova there is an attempt which we know is not easy, but maybe at some point will show will work, and will be able to get around this difficulty of studying the most interesting region. Okay. Now, if you remember, I had a page. I had in my summary of problem page. I had the what I call the hierarchy problem. What is this hierarchy problem? It's the problem that we cannot calculate in the standard model the mass of the Higgs. The mass of the Higgs, you probably know, is 125 GeV. The proton mass is a little bit less than 1 GeV, so it's 140 times the mass of the proton, mass of the Higgs. Now, that is a parameter in the standard model. We cannot compute it, and we cannot compute it even because it's one of those parameters that, as I told you at the beginning, absorbs divergences, right? So if a parameter absorbs divergences, it's obvious that you cannot compute it. So in the standard model, you cannot compute it, right? What is the hierarchy problem? So in a sense, in the standard model, there is no problem. There is no hierarchy problem in the standard model. Simply, we cannot compute the mass of the Higgs. So you remember the parameter, the potential of the Higgs, right? Potential of the Higgs has this crucial m squared term, which is essentially the mass of the Higgs, okay? And to try to compute it, you have to enlarge the standard model and make the mass of the Higgs function of some measurable parameters. Otherwise, the standard model, as I repeatedly said, is not capable to describe it. And the problem, the hierarchy problem is illustrated in this plot, you see. So the parameter space alpha beta is the set of parameters that enter into the calculation of the Higgs mass. Physical parameters, right, that depend on which theory I have in mind, but in any case, physical parameters. So imagine the space of parameters of this theory in which we try to compute the mass of the Higgs. Now, you see, there is, that essentially is the phase space of the Higgs potential, that plot, right? There is a line, right, which is called the critical line, if you want, that divides the region in which m square is positive from the region in which m square is negative, right? Why? Because if m square is positive, as you see it from there, h is equal to 0, right? So there is no breaking, right? So that the potential has the form in the middle there, right? V of h you see it, right? And h is equal to 0. So that is what happens in the region above the green line. Below the green line, the potential is, the mass m square is negative, so indeed you have symmetry breaking. But, if you try to compute that m square, when m square becomes negative, right, we get an abnormous value for the VEV, normally, right? So if we do it without being careful, right, we get an abnormous value for the VEV. VEV becomes, for the Higgs condensate, becomes 10 to the 19 GeV, which is a little bit higher than the observed value, 175 GeV. Okay, the observed value, which we get it from the Fermi constant, is 175 GeV, and you get an abnormously large value, right? So this is the problem, right? Of course, that doesn't mean that we cannot compute the mass of the Higgs correctly. The only problem is that we have to live very close to the critical line, to the transition line, in which m square passes from being large and negative and 0. Of course, there is a point at which m square has the right value by continuity, right? But you have to live very close to the critical line, right? And this, for example, is something that you can do there are people that study the Higgs phenomenon in condensed matter, right? And in materials, you can adjust the properties of the materials in such a way that you live on top of the critical line. Here, we don't have knobs. I mean, the parameters are fundamental parameters, and we are not able to fix them in that way. So this is the problem, right? Now, there are several solutions. I mean, the solution that most of us think and still think that it is, at least myself, I still think that it is the relatively best, is to simply add a step to this ladder, right? To add a step to this ladder, which is the step, you remember the key thing were symmetries, right? The key thing were symmetries, rotation symmetry, Lorentz symmetry, electroweak symmetry. Well, what you need to solve this problem is supersymmetry. Supersymmetry. If you believe that there is supersymmetry, you can solve this problem, right? And you probably have heard the statement that supersymmetry requires a doubling of all the particles of the standard model. The difference is that for any particle of standard model, you have to include a particle of different spin, right? Of different spin. For example, for an electron, you need to include a spin 0 particle, right? Spin 0. The E tilde is a spin 0 particle. And you have to do the same for all the particles. Now, there are people that object to this step because they say it's not economical. You introduce many new particles, right? No, this is not a good objection because, it's not really a matter of adding. I mean, the electron is always the electron, except that it is in a multiplet, right? Very much as it was in a multiplet when we introduced the spin, very much as it was in a multiplet when we introduced the positron, etc., or even the neutrino, right? You may wonder why we have still only one particle in each supermultiplet, and the answer has to do with the fact that all the particles that we see, which are the standard model particles, get mass from the Higgs. You have heard that, right? That Higgs is what gives mass to all the particles, except the Higgs itself. All the particles standard model, the massive particles, they get mass from the Higgs. If the Higgs value is 0, all the masses are 0, right? Now, against that, all the super partners, the E tilde is a super partners, don't get the mass from the Higgs. So that is the definition of what is the particle that we have to see and what is the particle that we haven't seen, right? So there is a clear separation. Now, and you solve the problem of the previous page if you think that the mass of the supersymmetric particles, the one that you haven't seen, are of the order of the Higgs wave, 200 GeV or something like that, okay? Unfortunately, this is only a qualitative relation. In other words, out of this you cannot make the statement that you should see a supersymmetric particle below 200 GeV or 300 GeV. No, we cannot. We cannot because there are possible cancellations. But there is the general picture. And this is why people for a long time and they keep looking at supersymmetric particles and hope to see an event like this. Unfortunately, this is a simulated event, right? Nobody has ever seen nothing like that. And the question is where are they? And it's a valid question. It's a valid question. To me, it's a valid question. In fact, if this were the event, at the same time, you would discover supersymmetry and another dark matter particle candidate, right? Different from the action, right? Different from the action. But not mutually exclusive, not mutually exclusive. They could both exist. Now, you know, I have given talks like that several times, and the legitimate question is, I mean, should we keep looking? This is my attitude. So the question is, are there any strictly natural theory compatible with current data? Strictly natural theory means that you know, this equality there should be strict, right? H equal mass of the particle, right? And the answer is no. I don't think that there is any. There is not anymore. I don't think that there is. You know, some fine tuning, one says, has to be present. Nevertheless, I think that the problem remains there, and the search for top partners remains the key. Why do I say top partner? Well, in the case of supersymmetry, means the selectron, right? The partner of the electron, or in fact, the partner of the top, right? The scalar partner of the top remains the key. And in other ways to solve the problem, I think the searching for top partners, we know that there must be top partners, so remains the key. And even if there is no strictly natural theory, I believe that that search remains valid. I mean, people, since nobody has seen supersymmetry, people have come out with a possible alternative on which I think I cannot really insist. There is a way to hide these partners, which has several implications, but that's perhaps. Let me show you this plot, which you know, if you follow the journals, I mean the normal newspapers, you may have heard of it, right? Now, should I explain what this page is? You see, on the left, right, on the left, I have two plots taken in December 2011, which showed the first evidence for the Higgs, 2011, December 2011, in the mass region, in the correct mass region, right? In the 4th of July of 2012, that evidence became striking in both cases, right? And in the 4th of July 2012, the discovery of the Higgs was announced without any problem, okay? Now, these two plots from the same collaboration, the difference is that those were taken at in what is called the first run of LHC, 8 TeV, right? Here is 13 TeV. The same collaboration showed in the gamma-gamma channel two hints that are consistent with each other at the level that is not that different from the one that turned out to be a real effect. Of course, the big difference is that in the first case, we knew that there had to be something. In this second case, we did not. I don't say that that was unexpected, because you know I keep saying since 2012 at least that to me only one scalar doesn't make a lot of sense, right? So it's possible that we have seen the hints of a new scalar, and the interesting thing is that in 2 months from now, if everything goes well, we will know if this is a fluctuation or if this will be confirmed, right? So and of course the question that we can ask now, if real, who ordered it? But that is out of the scope of this general talk. Now, the last subject that I want to touch is another lack of calculability of the standard model, which to me, per se, says that the standard model is not the end of the story, right? Now, what I call the flavor paradox. You remember the lambda ij, psi I, psi j, h. Flavor is another way to denote generation or to denote replicas, right? The value is called flavor. The index height goes from 1 to 3 is called flavor. Now, you see, what has changed, I claim, with the discovery of the Higgs, that now we have a direct evidence for the physical reality of what are called the Yukawa couplings, the lambda I. You see, that form, lambda ij, psi I, psi j, h, implies that the mass, as I told you, the mass of the particles, let's talk of the fermions here, but that's true also for the gauge boson, the W and the Z, but the particles get mass from the Higgs wave, right? H with the symbol like that is called Higgs wave, okay? So Mi equal lambda I V. So if I tell you the coupling of the Higgs to the particle I, the coupling is called lambda I tell you the mass. The mass Mi is equal lambda I times V. This is a prediction of the theory, okay? Prediction of the theory. Now, notice what came out of these measurements, right? You see, on the horizontal axis, I have the masses of some particles. You can recognize the top, the W, the Z, the bottom, the tau, and even the muon. For the muon, there's only a bound. So, on the horizontal axis, you have the masses of some of the particles, the heaviest, right? Because are those with the lambda I, which is big. And on the vertical axis, you have the lambda I, right? You have the lambda I, and as you see, they stay exactly on a single slope, right? Which is the Higgs wave, all right? You see that. So I claim that we are seeing the lambda I's. The lambda I's, I used to say, have become a piece of physical reality, right? We have seen them, and we can truly say that if lambda I is the coupling of the I particle to the Higgs, the mass is lambda I times V, right? Now, what is the problem? So, piece of analysis, what is the problem? The problem is that all of the lambda I's are parameters in the standard model. So, we do not have, I think I can say that, we do not have the slightest idea of how to calculate those lambda I's. Lambda I's are all parameter, and a colleague who is better than me in making plots has tried to reproduce the variety of masses, hence of lambda I's, right, for the various particles. You see, these are the three generations, right? You recognize the top, the charm, the up, etc., right? And notice that to be able to make a plot, this poor fellow had to rescale various parameters by factors of 10 to the something, right? Otherwise, you would not be able to show that. Now, those are all parameters of the standard model, right? And to me, this seems to me that this is per se is a lack of calculability, which shows that the standard model is not a complete theory. Obvious, right? I mean, this is a major problem of the standard model. There is no contradiction with experiment. There is no contradiction with experiment. We are not able to compute the particles of the masses of the elementary particles simply, right? The masses that I had in the first page. Now, I even dare saying, I know that I can be shown wrong tomorrow. I even dare saying that unless we find some deviation in flavor from the prediction of the standard model, it will be difficult to make progress. So I myself, since long time, follow quite closely the data, measurements in flavor, right? Now, of course, this would require a seminar per se, but I want to show you another kind of, in a sense, similar to the putative resonance at 750 GeV that I showed before, right? Is another putative problem of the standard model. You see, this is a collection of data. So, first of all, we are talking of the decay of the B. B is an hadron that contains a B quark that decays into a Cham quark, making a tau in the neutrino. And what the experiments do is measure the ratio between that decay and the decay, similar decay, in which instead of the tau you have the electron or the muon. Even mostly the muon, actually. The electrons are more difficult to catch. All right? And if you take the ratio is absolutely well predictable in the standard model. There is absolutely no problem. And this yellow line there, you see, the yellow line is the prediction standard model, and the largeness of the line is the error by which we are able to make the prediction. And consistently, all the experiments are on the right side. And there are, as you see, four different experiments made in three different facilities in the world, okay? Even conceptually different. And this is another way to show, in fact, I have added not only a vertical but also an horizontal line, which is the decay, you know, in one case there is the decay into a D, in the other case a D star. So, but those are details which are understandable. But the essence of the problem is that the prediction of the standard model, as you see it, is this little ellipse, very precise, and the average of the experimental data is pretty separated, and you know, people say that it is a 3.9 sigma deviation. Of course, you know, you should know that this is not the first case. There have been other cases in which people have seen deviations. I mean, the reason why I insist on it is because my view since long time is that the third generation is different from the first two, and in that decay there are three third generation particles and one second generation particle. So it's a special case which to me is interesting. We will see. Yes, there is lepton flavor violation is another case of interest, but perhaps I don't want to exceed my time. So yes, I want to you see, in terms of proposing possible movement for the future, right? So here I address myself mostly to my colleagues, right? You see, I told you that we have a test of the of flavor. We have a significant test of flavor. We see the lambda i's, and we see what are called the flavor change neutral current loops. We see effects which are characteristic of the theory at the level of 20% now, which is about the same level at which we see the famous electroweak precision test, a level of 20%, okay? Now, I claim that it is possible to try to go from 20%. 20% is not enough for the standard of particle physics. And since I told you that for me it's essential to see a deviation in flavor, we want to make progress, to me to be able to go from 20% to 1% would be very, very important. Now, there are people who think that would an experiment capable of exploiting the full luminosity of flavor physics be conceivable? You see, nowadays, LHC makes measurement, and there is even a dedicated experiment in flavor at LHC, okay? They are limited by the fact that they are unable to collect all the possible data and analyze them quickly enough. Let me put it like that for non-experts, okay? Now, there are people who think that progress in the direction of increasing the number of data that one can analyze quickly is possible, and that is probably a way to make experiments capable of exploiting the full luminosity of flavor physics at LHC, which would mean to be able to analyze 100 times more events than the one that people have. Now, this is more for experts, but I claim that this is a possible direction in which even the LHC could go. say, in the next decade. All right. Excuse me for keeping for so long. Well, this is the summary. As I said already, the standard model is not a complete story. We don't lack pictures that go beyond the standard model. I mean, it's a fact. Supersymmetry is one example. There are others, right? But fair to say, we don't know which one is right. And the problems are there. Some solutions are there. I think that there are even coherent solutions of most of the problems. But from that thought to the proof that we are right, there is still an important step to be made. Perhaps the most important statement in this page is the one that a comment that I already made almost at the beginning, right? The very nature of particle physics requires many highly diverse frontiers of research. As I said, this has always been true, I think, in particle physics, precisely because particle physics is a synthetic piece of science, okay? So that requires that you look in many different regions, and in particular, as I said, I think one should not identify particle physics with the high frontier, the high energy frontier search. The last statement seems to be in contradiction with the first, right? I mean, how can you say that the standard model is not a complete story and still say that the standard model will stay? Well, will stay. You see, at some level of approximation, I think it's clear the standard model is the correct theory. Nevertheless, it is true that it has to be improved in the many directions that I have told you. Okay, thank you very much.
Thank you, Barbieri, for this nice and clear talk. And please, do you have some question?
Can you compare all this charge asymmetry between this neutrality of matter, I mean, between proton and electron, the 0 point that... Yeah.
I mean, charge asymmetry is one of the elements that we'll have to enter in explaining what is called matter-antimatter asymmetry, right? Charge asymmetry, this CP asymmetry, okay? This is here. We'll have to enter as an explanation to explain matter-antimatter asymmetry. But per se, for example, the action solution of that problem has nothing really to say on that issue, right? But it's true that the violation of CP is one of the ingredients to explain the matter-antimatter asymmetry in the universe, and as you may have seen, it's indicated as one of the issues that the standard model cannot account for, because even though in the standard model there is CP violation, right? So in principle, the standard model might be able to explain the matter-antimatter asymmetry in the universe. Detailed analysis shows that it's not possible. In standard model, although there is CP violation, in principle there are all the ingredients, but you cannot get the observed matter-antimatter asymmetry. So that's one of the reasons that requires an extension of the standard model on which I have not commented upon. Yes.
And I understand that you still like a lot of supersymmetry. How much do you bet if at ACC in the next round will not find anything?
I frankly don't know. As you have seen, it's true. It's an ideological view, and I suppose you are a physicist sitting here. Sorry, I don't know you directly. I don't want to offend you, but as a physicist, ideologies are not enough. So it's true. It has become more an ideological issue, right? It's true that if there are other instances in which this concept of naturalness has played a role in physics in the past, and one can enumerate them, right? But I don't want to do that now, in which the solution of the naturalness problem turned out to be strictly natural, right? The mass of the electron, the self-energy of the electron, the electromagnetic self-energy electron, the K bar mass difference, the pi plus. So there are several examples in which insisting on this comment of being able to compute the quantity in terms of some new physics showed that the new physics was exactly there where you expected it, strictly natural. This doesn't seem to be the case for supersymmetry, so it becomes subjective to tell whether one should or one should not see supersymmetry at LHC. And as such, why should I tell you what I am ready to bet?
Commenting on that, sorry. I think the current limit on stop is greater.
Sorry, where are you? I want to see you.
Here,
yes.
Sorry. The current limit on stop mass under certain assumption is 800 GeV or even more. About that.
Which particle?
Stop.
No, the top is...
the stop.
Oh, the stop.
The scalar top, the partner of the top.
The stop,
yes.
Well, yeah, there's a lower bound, yes. The lower bound that you can discuss.
It depends on the assumptions.
Yes, yes.
I know because I ran that analysis.
Yes.
What would you do of a 1 TeV stop if we discovered it in a month from now?
I would claim that it solves the hierarchy problem, right? Because I recall you, right, that we are after understanding why V is not 10 to the 18 GeV, right? So, I mean, a stop of 1 TeV would mean that naturally V is of the order of a TeV. Well, it's observed at 200 GeV, right? 175 GeV. So, what's the problem? It would still be a major solution of the hierarchy problem. No problem, no problem. Unfortunately, I mean, the counterpart of that is that we are not able to tell you should find the stop below 1011 GeV. We are not able to say that, right? But in terms of solving the hierarchy problem, that would still be a coronation of a way to think. Yes, absolutely, yes, absolutely.
In one of your slides, you shown this tantalizing parallelism between the situation, the quasi-discovery of the Higgs that we had in 2011 and the actual situation that we have with this strange object that we have in true photon.
You don't want me to tell you how I want to bet on the discovery, right? Like him.
No. The problem, of course, you know very well, the Higgs couples to a lot of things, almost to all the particles. Yeah. While at the moment, it seems that this object couples only to two photons.
No. You see, if there is any problem with this putative resonance at 750 GeV in the gamma-gamma channel, is that you can explain it in too many ways. So, no, that's not really a problem. The problem is that we have seen in the past several other cases in which, you remember before the discovery of the Higgs, right? There was evidence for a Higgs at 140 something, right? That was so no. I don't think that is a problem. No, I don't think it's a problem. I think that I am able to offer an explanation which makes a lot of sense.
If we find the things that couples only to photons.
No.
This would be a problem.
No.
To my understanding, but
I
maybe.
agree.
Okay.
I agree. No. You will have to see it in other channels.
See it.
Yes. And in fact,
the problem is that
my quote-unquote favorite explanation requires that you see it tomorrow. So no problem. Yes, no problem.
If I can add, the situation is not the same as for the Higgs in 2012, because then the evidence of the Higgs in the two gammas was marginal, but the evidence of Higgs into Z was much.
Not in December 2011. In December 2011.
Okay, that was not pretty clear.
Wait a second. The only quote unquote evidence was in the two plots of gamma gamma that I showed you, because you see there were no data, right? There were no data. You see, when you see a 2 sigma, 2, 3 sigma in gamma gamma, you do not have to pretend to see it anywhere else, right? Because gamma gamma is by far the simplest way to see it, right? So it's a matter of statistics. No. I claim that in December 2011, we can check that, but I am pretty sure that there was no ZZ in 2011. No. December 2011.
I doubt, because they said it's easier.
No, yeah, it's easier, but if you have the statistics, we agree. If you have the statistics, it's easier. But you need the statistics, which is not a minor...
So I didn't play the game. I think this 2011 example may be just an occasional effect that was completely meaningless from the statistical point of view. But they didn't check, so I cannot tell you about that.
No, but 2011, sorry, it was not a statistical fluctuation.
Yeah, you
it was confirmed. As a...
No, you may have that with respect to the sensitivity that you had at that time, this evidence could be just a statistical fluctuation.
Of course.
So there is nothing that...
we all agree on that. We all agree on that.
We all agree on that, but we didn't check whether it was the case or not, so I cannot answer that. My question was another one. You said that the criticism against supersymmetry, that introducing too many particles is nonsense. But there is another criticism which is on the same way from a lot of your colleagues, theoretician colleagues, is that you are introducing a lot of new or additional parameters, not particles. So if one theory explodes in terms of parameter, some of your colleagues don't believe that this
You know what? Excuse me. You could have said exactly the same for the standard model. In the standard model, you want me to tell you the lambda ij's, which are measurable, are 14 parameters. Why didn't you stand up in 1970 when people formulated the theory and said, look, this theory is unbelievable. There are 14 free parameters in the flavor sector. And, as I told you, you have a good case. It turned out that so far the evidence is positive. So you see, one has to be careful with the statement that if there are many parameters, the theory is not interesting. No, of course not. Of course not. As I said.
No, these were not new parameters.
Of course not.
The masses were essentially there. But
of course not. Excuse me. As I showed, you didn't follow me. Excuse me. Of course not. You know what? I think that I am using not the latest version of the. I'm sorry, but that's okay. Excuse me. One second. Right now, you see, that was the situation when the standard model was proposed. Okay, that was the situation, right? So, in fact, the particle didn't even exist. Right? Not only you had not measured the mass, they didn't even exist. You understand the meaning of that plot? Right? So, no, it's not true. It's simply not true. I mean, maybe the history repeats itself. In 73, we had, less than half of the particles that have been observed now, right? And nevertheless, we dared writing a theory for the standard model with a huge number of parameters that so far turns out to be perfectly okay, right? So, no, it's not true. I mean, these are counting of parameters and things like that. These are, I think it's better to insist on principles. And the principles that leads to supersymmetry is this one. Yes, it's this one. This is a very strong argument to me. You know why? Because you can say, look, but then you invent another symmetry and then you have another piece of the ladder. You see, the symmetry that you can describe in field theory are not infinite, unlike what you might think, right? And as a matter of fact, in many respects, that last step is, at some level, has to be there. Now, at which level, we don't know. But you should not, I don't think that the counting of particles is, I don't think that is a good argument against. And even the counting of parameters is not a good argument because the standard model is a counterexample.
Sorry, just to be precise, I clear up my mind since the objection of Sandro was just a few seconds before my intervention. In 2011, you're right, the gamma-gamma evidence was the one that stayed for all the time, but there was also a weak, but of same order evidence for X to ZZ.
Not in 2011. I don't believe
I remember the seminary was
I don't believe that, but that's okay. But in any case, you see, let me tell you, the essence of the problem is the following. I agree. If you want, I can show you my favorite theory to explain the gamma-gamma, and I can tell you that you are off in terms of statistics by a factor of 3 in order to be able to see the decay into ZZ, for example. You are simply off by a factor of 3 in statistics, right? So you are close, but you are off by a factor of 3. And that's why I said that by the end of August, not only we will know whether the gamma-gamma will be improved or not, but we should see if there is some other channel that shows up, right? So, I mean, you see, in fundamental physics, one has to be patient, right? And to wait until the end of August, I don't see it as a problem.
Yeah, Riccardo, you emphasized the importance of putting all the standard model problems on a single slide to try to exploit connections and have a global view. Don't you think that one could gain something by making a step further, include the gravitational interactions that after all are well known, and include also the other parameter that is 0 or almost 0?
I don't know if you have noticed, Fabio, you are right. I don't know if you have noticed that is mentioned, this problem, under 3, right? I mean, under 3, gravity, right? Gravity. You see, the Newton constant, the interaction of matter with G mu nu, with the metric, right, is a non-normalizable interaction. I mean, there is a coupling, right, which has the dimension of a mass to the -2, which means that the operator has dimension 6, right? So it's absolutely true. One should include, the fact that we do not, the standard model does not address the issue of gravity is another minus for the standard model. The reason why we have been able to survive so far is because, at the energies that we are exploring so far, there are reasons to think that gravity is irrelevant. But from a conceptual point of view, you are absolutely right, yes. Yes.
I was thinking also in terms of unnaturally small parameters, that even if you couple to classical gravity, you have the vacuum energy.
Yes. That's another problem. That's another hierarchy problem. Yes, that's another hierarchy problem. And for which, in fact, I'm not sure that anybody knows a possible solution, unlike the case and there are some people who think that the fact that you cannot solve one, but the other is a problem for the other. Let me tell you, my view about the cosmological constant is the following, that I am not sure at all that people have seen a cosmological constant, myself, I think, right? in the sense that, of course, I know that the universe is accelerating now, right? And I don't doubt of that, but I am willing to accept other explanation than a pure cosmological constant. So I still think in terms of the cosmological constant being zero. You might tell me that you still don't know how to explain why the cosmological constant is zero, and you are right, but somehow it seems to me that it's easier to explain a zero than 10 to the minus 30 electron volts to the fourth power, so yes.
So to ask you, you showed that the mass of the Higgs is close to the critical line. Do you think this has some special meaning?
No, we have to explain that. We have to explain that. No. I think that you refer to, maybe you refer to another issue which has been discussed in the literature, which is called the vacuum stability. Is that what you refer to?
Yes.
No, that's another issue. That's another issue, and people want to see an explanation of the fact that the Higgs is 125 GeV because of that. I respect that view, but I don't think that that is interesting. Yes, I have a page on that, but that would take a quarter to an hour to explain it. I tend to think that that's not an interesting direction. Yes, even though I know that people...
There are other questions? Otherwise, we thank Riccardo again.